Now the pipe designing is done. Now what we need to understand, or what we need to do, is how to design a pump. For pump designing, we need two major components, the parameter. Number one is flow rate. Number two is total dynamic head, or the head against which pump need to operate. Third is the specific gravity, but I'm not mentioning it here because by default we are assuming that we all are dealing with water. If you are dealing with kerosene, if you are dealing with the petrol, or if you are dealing with the honey or diesel, we need to take into account the specific gravity of that fluid in order to determine the pump capacities. But by default, if we are we're dealing with the water, so its specific gravity is 1, so no problem. What is worst case scenario? These are especially for those who are interested to go for the immediate after their graduation, if they have a desire to go in industries of irrigation system. Remember, the first question that the interviewer may ask you in your interview will be the worst case scenario. What is worst case scenario? Right? Worst case scenario has two parameters. Number one, high flow rate. Number two, far remote point. These are the two parameters for the worst case scenario in order to design the pipe size, or in order to determine the friction losses. We have two parameters. Number one is far remote from the pump. Number two is high flow rate, highest flow rate. Like that is the pump. These are the main and sub mains. That is zone 1 or V1. I mean valve 1. Valve 1 has to deliver 14,000 liter per hour. Valve 2 14,000, valve 3 14,000, but valve 4 have 15,000 liter per hour. So while looking at this case, I would prefer to calculate the friction losses for valve number 4 and forget about valve 3, 2 and 1, because we have highest flow rate and we have farmost point from the pump. Farmost point from the pump is V5, V4, right? And highest highest flow is for the V4. So I need to use the Hazen-Williams for calculating the friction loss in this zone or in this valve. So that the length will be from here to here, that is the length. Flow rate is 15,000 liter per hour. So these are the two, and for example, that red pipe indicates 3 inches piping. So we have dia, we have length, we have flow rate. We can easily calculate the friction losses. But remember, the F factor. F factor is valid only for the sub-main and for the laterals. For the main line, F factor will always be 1. Why? Because if we need to deliver at this point 15,000 liters, so from this you see there is no outlet. These are the valves available, but all these will be off, in off position, they will be shut, and because only one zone will need to operate. So the flow rate, if we needed 15,000 liter over here, we have to induct 15,000 liter from the pump. So for the entire length, the total flow rate will be 15,000 liter. But so we call it main. So for the main, the F factor in Hazen-Williams will be 1. For the sub-main, yes, it will be now less than 1. It can be 0.2, 0.355, depending upon that table or the equation that's mentioned Hazen-Williams in Larry. Sorry. Okay, so worst case is remote point and high flow. As I mentioned earlier, that it's a remote point V4 and the flow in V4 is highest. So we need to design the system. We need to design the pump for V4. So by the way, what happened? If V1 is 20,000 liter per hour and V4 is 10,000 liter per hour, then what about the worst case scenario? Now we don't have any perfect worst case scenario. Now we have to look for 2 points. Number one is V1 and number 2 is V4. Being a beginner, you have to calculate friction losses for a flow of, let's say, 20,000 liter per hour and a length of this much for dia 3. Then calculate for 10,000 liter per hour with this length, 3 inches. and then you need to see whichever is highest. And you have to pick the value which is highest. Remember, don't sum it up. It's not like that if in this zone we have 10 meter friction losses, here we have 12, here 14, and here we have 20 meter losses. So what we need to design the pump for is for the 20 meter only. We don't need to sum up 20, 10, 15 or something. So because all these are operating in parallel form. It's not in series. These are all in parallel. So it's very similar to the electrical circuits. In parallel electrical circuits, what remain the same? The voltage. And here in hydraulics, the voltage is potential basically. So here in hydraulics, the potential is head, the pressure. And in parallel, what varies is the current. And current in hydraulic is flow rate. So both are the same. Now another thing is looping of the system. For example, first of all, I would like to say why we need to do the looping. In previous case, you see we have only one main which being terminated here, and then we have a submain, right? But here we have a loop, the green line. We have no dead end. If we don't have any dead end in our piping network, we will call it a loop system. This is important for irrigation system design. This is important for public health. This is important for water supply lines, which is primarily done by the public health. Why we do looping? Number one, to reduce the cost of piping networks. Number two, to have almost the same pressure along the entire pipe length. What does it mean? For example, you design the system for this point, and here the friction losses or the total dynamic head that you have to maintain is around 20 meters, for example, at the pump. So what do you say if the friction losses from here up to here is 10 meters? So what will be the friction losses from here up to here? It will be higher than the 10 meter or lower than the 10 meter? It will be less than 10 meter. So what will happen? Here at this valve, the pressure will be higher as compared to this valve. Then again, the pressure at V2 will be higher than V3 or V4. And again, the pressure at V1 will be the highest because we designed the system for this remote area. So pressure at V1 will be highest from V2, V3 and V4. Now it may be a problem for you because in V1, in valve 1, the pressure will be highest, the flow rate will increase, it will disturb your irrigation pattern or irrigation scheduling, or it may disturb the piping networks, the pipe pressure rating of the piping network. So we have two options. Number one is to install PRV, pressure relief valve, and number two is, which I love the most, is, although it's a little high in cost, VFD, variable frequency drives. What variable frequency drive do is that it monitor the RPM of the motor, which in turn, due to affinity law, reduces the pressure and the flow of the pump. So in that case, we may have VFDs or pressure relief valve to account for the highest to the lowest pressure ranges. But here in looping, the main advantage is that pressure in the entire network will almost remain the same. Where we use it, as I mentioned earlier, in irrigation system, in water supply system, and especially in golf course irrigation. Because in golf course irrigation, we would have 10 acres or 20 acres land which need to be irrigated. So in that case, the pressure variation shall not be very high. So we go for looping system. In looping system, what we do, for example, look, the red represent 3-inch line and the green represent 2-inch line, right? In looping, we assume, and to some extent, just to simplify the thing we assume, otherwise it remains the same, that any flow entering in the loop will divert on either side in equal quantity. Like 22,000 liter enter into the loop, so to the left it will, to the right it will be 11,000, to the left it will be also 11,000. So now we need to design the system for 11,000 liter per hour, not 22,000 liter. So what will we achieve? That, for example, for 22,000 liter, keeping velocity at 1.5 meter per second, we need 3-inch pipe. But keeping the same velocity and while designing for 11,000 liter per hour, we need 2-inch pipe. Right? So the dia of the pipe will be decreased. And what next is that how to calculate the friction losses. So we need to divide the flow and we need to divide the length of the loop in two. For example, length of the loop is 100 meter, flow is 22,000. So in friction losses in Darcy-Weisbach, we will take 11,000, divide the flow by 2, and we will take length as 50 meter, divide the length of 100 meter, divide by 2. So half the length, half the flow for looping system, keeping the F factor 1. So now we have calculated how to design a pipe for a specific flow rate. Then we learned how to calculate the friction losses for using Hazen-Williams equation for a single pipe. Then we learned how to apply the F factor for multiple outlet pipes. And then we understand and we try to learn about the looping system and the telescoping of the pipe. So now, why, by the way, why we are doing all these things? Because we need to design a system which can operate or which can meet our specific job or task. So TDH is total dynamic head. TDH is total dynamic head. Whenever, and contrary to the TDH, the term is total static head. Total static head is the one where there is no flow. When there is no flow, we call it total static head. And when there is a flow, it's called total dynamic head, and the difference between the two is the friction losses. Because if there is no flow, there is no friction losses. And whenever there is flow, it will be offer resistance by the pipe. So that is what we call it, head loss or friction loss. So that is the basic difference between the TDH and static head is the friction losses. So TDH is major friction losses using Hazen-Williams formula. Minor friction losses, remember we will discuss it later on. Suction head, nozzle head, elevation differences or any other loss might be due to elevation or due to some other physical structure within the system. So it is called TDH. What is this minor? We have calculated friction losses in piping network, but in piping network, you must know there are elbows, there are T's, there are reducing bushes, sudden contraction, sudden enlargement, there are valves, a barb connection of the dripper or the thread connection of the sprinklers. All these we call it minor friction losses. So we have the formula how to calculate these minor losses one by one, but being a practical person, being in field, and as I mentioned in the start of the training that I'm not here to teach you the theories, I just want to give you the practical approach, the concept of the system. So we take minor losses, we take it as a 20% of the major losses. That's simple. If friction losses, major friction losses is 10 meter, so minor losses will be how much? 2 meter. What is suction head? Suction head is basically the vertical, the vertical difference between the impeller eye and the water table or the water level. that vertical height, it can be 6 meters at the most that we recommend. Most of the time in Pakistan, unfortunately, you can see even 7 meters, even 10 meters, you can see it. But in that case, pump will cavitate, there will be cavitation and all that. But practically, we take it as 5 to 6 meters, not more than that. So that will be the difference, the elevation difference between the impeller eye and the water level. It is suction head. Nozzle head, like if you are installing a drip irrigation, so at the particular dripper, you need 10 meter nozzle pressure. If you are installing the rain gun system, for example, it varies, but minimum we design it for 30 meter nozzle pressure. So that nozzle pressure is separate. That I mentioned earlier that we want to give it a velocity head. So that velocity head is basically 30 meter head, which is being converted to velocity head, and then we get the throw, that what we need. And what is duty point of the pump? So in pump, there are 3 parameters, but as we are dealing with the water, by default I assume that we all are dealing with the water, so I've eliminated the term specific gravity. So then we are left with total dynamic head and the flow rate. Whenever you design a pump, you ask the manufacturer that I need a pump. If the manufacturer is a professional and if they are technical, they will ask you a question, what is your duty point? So you must know that what is a duty point. Duty point is the point at which you have designed your system for 2 parameters. Number 1 is head, number 2 is flow rate. So you have to give the manufacturer 2 parameters, that I have this much flow and that's my head. Please suggest me a pump. Then he will give you a pump that's, okay, you go for this model with impeller size of this and that. Also, they also provide the pump curve. You can select it from that. And in almost, I think, a year back, we have a training on the pump selection as well. So all that material is available on my website. You can get it from there. Or otherwise, you can ask the manufacturer what pump size do I need.